This is Mr. M for Chem, Introduction to Organic Chemistry. Here we can see Damien Hirst's $100 million skull made from diamonds. Diamonds are a extended carbon-carbon catenated. Catenation means carbon to carbon to carbon to carbon. Giant covalent structure manifesting in a beautiful crystal which does things to light, which bedazzles humans. Whether this is tasteful or not, I will leave that to the experts. Who is this video appropriate for? It is appropriate for IB kids, A-level kids, HSC, and dare I say AP kids, as well as a general overview of organic chemistry, one of my favourite things on the planet. Okay, so let's get my windows sorted a little bit here. We're going to start off just by recalling what is a covalent bond. Well, a covalent bond, as you all know, is the attraction between neighbouring nuclei and the bonding pair of electrons intermediate between those nuclei. Here we have hydrogen. Here is the hydrogen proton in the nucleus of each one. And the bond length is going to be half the distance between adjacent nuclei. So that definition, let's keep in the back of your mind. That's really important to know. Another thing which they love to ask you is about valence shell electron pair repulsion theory. And if you're looking at alkanes, it's always going to be the tetrahedral, which is down here, basic geometry here. If it's the carbonyl group, we're looking at 3 electron domains, which will normally be trigonal planar. So I'd say 90% of cases, your geometry is either going to be 109.5 degrees around a central carbon, or 120 degrees around a carbon, which is either doubly bonded in an alkene to another carbon, or doubly bonded to an oxygen in a carbonyl group. So for instance, in ester or carboxylic acid, aldehyde, ketone, etc. So your bonding knowledge really comes into play in organic chemistry. Okay. Carbon atoms make strong covalent bonds with each other. They do because they can hybridize. Remember, if it was a tetrahedral, what's the hybridization? Yes, the hybridization will be sp3, and you need to do the electrons in boxes. Do your ground state carbon, 1s2, 2s2, 2p2. The 1s, don't forget, is buried too close to the nucleus to get involved in hybridization, but the 2s and the 2p come together. One of the arrows in the 2s2 box, the electrons, jumps into the pz. Those orbitals come together and you get S1p, 2p, 3p, sp3 hybridization, which would be the tetrahedral 109.5 degrees. sp2, the pz is unhybridized, but the 2s still hybridizes with the first two p's, the px and the py, but the pz is unhybridized. That makes the pi orbital. Okay, so the hybridized are the sigma bonds, the unhybridized is the pi bonds, as you know. So these two shapes here, you need to keep in the back of your mind. Carbon will do lots of single, double and triple bonds. It's quite happy to do any of those. We can have straight chains, branched chains, we can have rings, we can have multiple rings together, we can have straight chains branched off a ring. The possibilities are endless. There's no end to the number of carbon compounds that we can make. Okay, it's mostly carbon and hydrogen. We do have quite a bit of oxygen and nitrogen and some sulfur now and again, and organometallic chemistry is another rich area, not in this video, not on the IB. Okay, so groups can be in different positions on a carbon skeleton. We kind of know that, don't we? So what's important about carbon? Well, carbon is unique in its ability to form stable compounds when bonding with itself in extended networks. You might think, well, in the same group 4, group 14, what about silicon? Well, silicon can do that as well. But look at the bond enthalpy. Carbon-carbon is plus 348 kilojoules per mole, so it costs me 348 kilojoules per mole to break that carbon-carbon bond. But to break the silicon-silicon bond, it's less than half. Is that less than half? Yeah, okay, 3. So it's less than half as much to break a silicon-silicon bond. So carbon compounds are really quite stable, which is why oil comes out of the ground as a stable compound. We can have straight chains or rings. We could make, I don't know, let's have a bit of carbon here. We could make, the first one, the second one, the third one, the fourth one, the fifth one, 6, 1, 2, 3, 4, 5, 6, 7. So we'll make the alkane with 7 carbon atoms. You all know the name of this one? Of course you do. Let's just clean that up. There we go. The name of this is heptane. Okay. All the bonds are single. They're all sigma bonds around each carbon. The bond angle is 109.5 degrees, and the hybridization is sp3. All of these are covalent. Clearly, it's purely covalent between adjacent carbon atoms. There's a very, very slight difference in electronegativity between carbon and hydrogen, but nothing to get excited about. So that was 7. We could even put those 1, 2, 3, 4, 5, 6, 7 carbon atoms. We could put them in a ring, and this would be cycloheptane. Never come across this in a cupboard, but it's carbon, so we can make it. We can spin that around, have a look along the axis. It looks quite a strained molecule to me. Okay. They can be in straight chains or they can be branched. We could get a nice cyclohexane structure, and we can put atoms either substituted on the ring or substituted within the ring. Let's clean that up. There we go. Get my periodic table, and let's have some chlorine. Chlorine's a nice one to put on, so let's make this one. Okay, so that's chlorocyclohexane, or 1,2-dichloro, or 1,2,3-trichloro, and we can spin it around. And clearly this is a highly polar molecule, and we can have a look, just see where the electron density is in this molecule, and we should see large areas of electron density, as we do around the top of this molecule. Look at that, it's glowing red around the chlorine atoms, where comparison it's only kind of greeny yellow around the hydrogen, showing the much higher electronegativity here. Really, the possibilities are endless. We can have multiple bonds. Multiple bonds is not a problem. Okay, so we're going to have carbon, 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 and clearly we have ethane, and we have ethene with a double bond, a sigma and a pi, and we have ethyne, which is 1 sigma and 2 pi. Let's clean those up, add the hydrogen, and we can move those around. Okay, so there's ethane, ethene, ethyne. When you look at them, you should see ethane, sp3, 109.5 degrees around each of these carbon atoms. sp3, and then you should see sp2, 1 sigma, 1 pi, trigonal planar, 120 degrees, and then ethyne, you should see sp hybridization, and this is linear, 180 degrees. So you should always have that at the back of your mind when you're looking at these molecules. Why? Because that gives you a really good insight. If you understand the story behind it, it gives you a really good insight in working out what the products are going to be as we get deeper into organic chemistry. So the basic atom is hydrogen with carbon. We can also have oxygen and nitrogen, and halogens and sulfur are very common. There's lots of them. Here we have 1, 2, 3, 4, 5. So the longest chain is pentane. Blue is nitrogen. That's NH2. So that's 1 amino pentane, or pentylamine, I suppose would be acceptable. Oxygen to hydrogen is a hydroxyl group, which gives us the alcohols. So this is going to be 1, 2, 3, 4, 5 pentan-1-ol. We'll do some more naming shortly. Things can move around. Okay, atoms can be placed in different positions on a carbon skeleton, so you don't know which one you've got without seeing the displayed formula. Okay, so this one is, well, what is it? Is it the same as this one? Just put my single bonds in. Clean that one up. Beautiful. Are those two the same molecule? Talk amongst yourselves for a moment. They are both 1, 2, 3, 4, but 1, 2. They are both but 2-ene. On the slide we have pent 1-ene and pent 2-ene. These are both but 2-ene, but you can see the methyl groups are on the same side as the double bond on this one. But here the methyl groups are on adjacent or opposite sides. So this is cis but 2-ene, and this is trans but 2-ene. So we can have geometric isomerism with the same molecular formula. The double bond could be here, 2-ene, it could be here, 1-ene. If we have a halogenoalkane, 1, 2, 3, and then let's have some, should we be exotic? Let's have some astatine. I never played with an astatine atom before, why not? So just tidy that up a bit. Carbon to astatine. Good, clean that up. I guess we have 2-astatopropane. 2-astatopropane. Forgive me if that pronunciation is incorrect, but we could also have 1-astatopropane. There's no more possible than 1 and 2, because clearly here is still 1, because it's the longest chain and the lowest number that we are using. Okay. So there are 4 types of formula. There are actually a few more different types of formula, and we can have molecular, empirical. Empirical is the simplest ratio of atoms in a molecule. So the example here is C4H10. What's the lowest multiple? It's C2H5, because we can have C2H5 is the lowest, we can have C4H10, C8H20, and so on and so forth. So the empirical formula can give us some insight, and we can use that to work out the molecular formula if we know the molecular mass from mass spectrometry, but let's not go there, we'll save that for a different video. See, given the empirical formula, C2H4O, that doesn't tell me enough. It doesn't tell me enough. It tells me there's some carbon, some hydrogen, and some oxygen in this ratio. That's all it tells me. The molecular formula tells me C4H8O2, but it doesn't tell me how these are bonded together. The condensed formula, this looks good. So CH3, CH2, CH2, COOH. So that's 1, 2, 3, 4. Don't forget the carbon in the carbonyl group. So that's going to be butanoic acid. It smells like dog poo, horrible stuff. The displayed formula, even better, I can see my CH bonds. I could have worked them out from the condensed formula, but clearly this is C double bond O, carbonyl to OH, carboxyl group, so it's a carboxylic acid. The structural formula, slightly shorter than this one, and then the much loved skeletal or skeletal formula. So my students always ask me, well, is that a skeletal formula of methane, sir? I suppose it is, but we're not that lazy. Okay, is that a skeletal formula of ethane? Yes, it is, but still we're not that lazy. But when we start to get longer and longer molecules, we do as chemists. I mean, this is why I love WebMo, because it fills in the hydrogens for me. We do kind of get a bit fed up writing CH. Okay, let's put that there. Let's do an oxygen there, and let's have hydrogen. So the valency of carbon is 4, always 4, never less and never more. If you've got less or more than 4, it's going to have some sort of formal charge on there. So now we've made 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So this is heptanoic acid. Heptanoic acid. I've never seen a bottle of that. I'm sure it exists. Okay, heptanoic acid. But we wouldn't know the connectivity. We wouldn't know if this methyl group was branched here just from the molecular formula. We need to see the structural formula or the displayed formula to have a Scooby-Doo about what the actual molecule will look like. The cyclical structures, these always entertain students. So clearly all I have to do is obey the rule of 4, always 4, never less and never more. And here I've made some cyclopropane. This is unhappy carbon. It's unhappy. This is something called ring strain. Okay, this is a quite high energy unstable molecule. It will readily fall apart. Why? because carbon wants to be 109.5 and we forced it here to be 120. It's like, ouch, don't like that, want to break apart. So a skeletal formula is used to show a simplified organic formula by removing hydrogen. So this hexagon here is great for cyclohexane. We could just do a triangle for cyclopropane is my point. Thalidomide is a classic drug which was prescribed for morning sickness for pregnant females in the 1950s and early 1960s. The US was the only jurisdiction on planet Earth which said no, we're not allowing you to sell thalidomide to our pregnant mums. Europe said yes, you can, that's okay. But what happened was that there is something called an optical isomer of thalidomide, and one of the optical isomers did cure morning sickness and was a very effective drug, but the opposite isomer of exactly the same formula created teratogenic birth defects, and the effects are still felt to this day. So our humanity's playing with organic chemistry has had some quite serious, in fact in this case catastrophic consequences without our actual knowledge of knowing just how these molecules can manifest themselves and interact with the human body. So organic chemistry, the power to cure and the power to change fundamentally, in this case DNA. Okay, general formula. Homologous series will differ by a CH2 unit. That's a definite thing. Learn it, deal with it, move on with your life. Members of the same homologous series differ by a CH2 unit. Same general formula, differ by CH2. Same functional group, so in this case the hydroxyl group will denote the alcohols. All of these are alcohols: methanol, ethanol, propan-1-ol. You can have propan-2-ol as well. It'll all behave similarly chemically. Again, it's a gradation in physical properties, boiling point, melting point, as we increase that hydrocarbon chain, because we are increasing the van der Waals forces of attraction the longer it actually gets. Okay. Functional groups. The functional group is the thing that's going to determine the chemistry predominantly of the molecule. Okay, so we classify organic compounds by their functional group. At the bottom here, we can see it's an amine, so that's 1, 2, 3, 4, 5, so that's pentylamine or 1-aminopentane. And here we have pentan-1-ol. Okay, they both have pent, 5 carbons with hydrogens attached to the valency of 4, always 4, never less and never more. And there are a bewildering, this is just the beginning, example of common functional groups. Because the list is so vast, I wouldn't recommend you actually sit down and learn these with a set of flashcards. Okay, the common ones that you should recognize are the alkanes, the alkenes, the alcohols, the aldehydes, the ketones, the carboxylic acids, the amines, maybe the amides, carboxamide, ethers don't come up much on IB, and everything else you can kind of ignore. I'll be as brave on that one, so you can almost ignore that. So yes, no. Acyl chlorides, A level, yes. IB, no. Amides, yes. Esters, yes. Nitriles, yes. Amines, yes. Nitro, yes, with benzene. Sulfonic acid, no. Ether, so. So they kind of come up in questions, but you've never been asked to name one for the IB. Okay. As you practice more mechanisms and do more organic chemistry, you will naturally, as a consequence of learning it, learn the functional groups the more that you do. I think it's not a standalone thing. You learn them as you go along doing the mechanisms. Okay. You should recognize most of these. You should know to count to 4 and recognize that if your carbon has less than 4, it should have a charge on it, or more than 4, it should have a charge on it, or you're just wrong. Know that much. So here, we're going to break for a minute. You're going to look at this slide, and I want you to work out how many structures you can make from the formulae, the molecular formulae on the left hand side. Pause the video now, I'll give you the work solutions. Welcome back! Wasn't that fun? Did you get all of them? Happy days. So, organic chemistry. Beautiful. Carbon, hydrogen, nitrogen, oxygen, bit of sulfur now and again. Formulae only give us so much information. There are so many possibilities. Oxygen always 2, carbon always 4, hydrogen always 1. Stick to those rules, you can't go far wrong. How do we find out then, given a random powder, what's in it? We could burn it, do a combustion analysis, but that's kind of old school. We're quite sophisticated now. We have some wonderful instrumentation. You might have some at your school. An infrared, we don't have one of those. A nuclear magnetic resonance spectrophotometer, we don't have one of those, but I'm working on it. We also have gas chromatography, we have one of those. And we can look at the spectra of compounds and compare them with reference spectra. And we can qualify and quantify what we have. For instance, I don't know, testing for drugs in sports, or when you're at the airport and they scan your talcum powder, that's probably GCMS, gas chromatography mass spectrometry, to find out that it is talcum powder. Okay, I hope you enjoyed that little whistle-stop tour over the beautiful world of organic chemistry. Hope it's given you a bit of inspiration, a bit of fire to continue doing some more. There will be more videos. Again, a huge thanks to Knockhardy Publishing for allowing me to use this PowerPoint. The link is at the bottom of this video if you want to look at the rest of their fantastic PowerPoint work. You know what to do now. Smash that button. Thanks so much for watching. Have a great day. Out of here, Mr. M for Chem. Thank you.